Hi everyone, I'm Ashka. I'm in Catalyst, just like everyone who's teaching this course. I'm a junior, and today we'll be talking about graphs. So last week you guys talked about trees, and graphs are pretty similar to trees. So before we delve into like the specifics of graphs, can anyone give me a guess about what is a graph and how it's different from a tree, for example? Yes, Joanna.
A graph has like vertices
Uh
and
huh.
edges,
Uh huh.
and it's different from a tree because the vertices and edges can all interconnect and point to each other. Or
Okay.
vertices can point to like several different edges.
Right.
Wait,
Right.
edges to
Yeah.
edges.
Yeah, so you're on the right track. So basically, Joanna said like you could have like more like a graph is basically a tree, but you could have more diversity in terms of edges or where they're doing or what they're doing in particular. And basically, what she said, a graph is a set of vertices or nodes which are connected by edges. So you may ask, how is that different than a tree, is what we talked about last week. So here's kind of, I have 2 pages of like a screenshot basically of telling you the differences. So for example, a tree, which we talked about last week, is a minimally connected graph. Okay, so you have any two vertices, you'll have one edge connecting the two. So you won't have a vertex, or you won't have an edge that has direction going from A to B and B to A. But in a graph, you could have not only that, but you could also have different ways to get to different vertices rather than just like one path. Another thing is that trees, what we talked about last week, don't have loops or circuits or self loops. A loop is basically you might have A, B, C, and maybe C is connected to A, and you can just keep going in a circle. A self loop is A is connected to A, aligned to itself. Um, and graphs can have loops, circuits, as well as self loops. And then a root node in the graph, which we're going to talk about this week, there's not really a concept of a root node because it's just like a graph. So you can think of a graph as like how Facebook represents like nodes of people and their social networks. On the other hand, trees have a root node. So when we talked about the algorithms we talked about last week, there was like a starting point. Usually, if we want a starting point in graphs, we ourselves have to set that starting point and find that starting point. So that's kind of the basis of some different algorithms that are talked about in more advanced graph theory. Um, Additionally, just to, I guess, sum up the rest, last week we talked about pre-order, in-order, and post-order traversal. In graphs, it's primarily two different types of traversals called breadth first and depth first, which you guys may have heard about before. Um, and I guess the rest of this is not too important right now. And just to, I guess, a little more detail, some things we talked about last week were like BST, binary tree traversal, things like that. For graphs, it's mostly directed and undirected graphs, although there are a little bit more nuances, which we'll get to in a second. And on top of that, uh, yeah, that's basically what we're going to cover. But if you guys want more detail, you can look this up as well. Okay, so in short, a tree is a restricted form of a graph. So a graph is like has more complexities. Um, so there are a few different kinds of graphs. First is an undirected versus a directed. So can anyone like kind of give a guess as to what those two are, or what's the distinction there? Yes.
In the directed graphs, each node has a direction which it's pointing to, but in
Mm-hmm.
undirected, you go either way.
Yes, yes, exactly. So, do you have, what's your name, by the way?
Daniel?
Daniel? Okay. Do you have maybe an example of a real world application where maybe one situation would use a directed and another would not?
Um, so I guess in an undirected one, it could be like going from one city to another.
Mm-hmm.
Um, in a directed, it could be kind of like a network
Yeah,
of
yeah.
connections.
Basically, yeah. You could have like a lot of different applications. Like what you said, like a road, for example. You can go both ways on a road, right? So you could have like a map that has undirected edges. Say you're trying to model Twitter, you could have directed edges because like a lot of people follow one person. That doesn't mean someone follows them back. Things like that. Cyclic or acyclic? Anyone want to give a guess? And we kind of covered it a little bit before. it's kind of self-explanatory, so we don't have to really cover it. But like basically, cyclic means you can have cycles. Acyclic means no cycles. So how would a cycle appear? When you have maybe like nodes that are connected, and the end node is connected to the start node, for example. Weighted or unweighted. That's just how it sounds. Weighted means like edges have weights, and unweighted means they don't have weights. They're all the same. So say if we go back to the map example we kind of just covered with the undirected graph, you could have a network. Say you have cities represented as nodes and edges representing roads. You could have maybe the time it takes to travel from node A to B or city A to B represented by the weight of the edge. So say you have like one weight that's 100, but then you have like 10 little nodes on a path that are all weighted 1, that would be faster to get to the end node, for example. So that's also the basis of some algorithms that we probably aren't going to cover today, but you will see in 330 if you're a comp sci major. And yeah, so those are basically the different kinds of graphs you can have. Some additional vocabulary are adjacency and neighbor. So basically, like a neighbor of a node is something that's connected to. It's not really the concept of like when we had a tree, you had children nodes. You could have them, but they're mostly referred to as neighbors just because that it's like, since you don't really have a start, sometimes you may not have a direction, but in the case you do have it, then they would be children. Degree means how many edges a node has that's going out of it. So you could have like a node that's connected to one thing versus 10 things. So those are differing degrees. And same thing with a loop. We just covered a loop earlier as well. So this is like not very important to interviewing in particular, but I guess it's just good additional knowledge to have, and especially if you're taking 230 and 330, you might cover this, especially in 330, I guess. But basically, you can represent graphs two different ways. One is a matrix and adjacency list. Adjacency matrix is basically having an array where it shows every item in the double array is corresponding to two different nodes and the connection between them. So it's just a boolean array. 1 means there's an edge between them, and 0 means there's not an edge between them, if that makes sense. And then you can also have an adjacency list that's mapping the same exact thing to find the edges. You just have like the number of lists you have and the number of nodes you have, sorry, and the ith item is telling you if there's an edge between that node that owns the list and that represented node, if that makes sense. That was kind of a weird way of me to say it, but if you have any, does anyone have questions on this right now? Yeah, okay. So BFS and DFS, what do they stand for? Correct. And can anyone tell me, I guess like two people, what is BFS and what is DFS? Which we're going to cover today, so if you don't know it, that's okay. Yes, Daniel.
So for BFS, it goes layer by layer,
Mm-hmm.
and then for DFS it goes as far as it can, and then slowly backs back up.
Yes, yeah, basically. So, some important things to know with the BFS. One thing is we would need a Boolean array, not necessarily a I missed a quote, but a visited array basically. So why would we need that in a BFS if we're going with the definition that Daniel said?
So you don't revisit a node again.
Mm-hmm. Yeah. So why would that be a problem? Like,
You get caught in a loop.
yes. Okay. So you're saying basically Simran said that you can get caught in a loop if you don't keep track of what you've already seen. So you could go A to B, and then say B is connected to C, C is connected to A. You'll go back to A, and then you'll go back to B, rather than knowing you've already seen it and terminating then. So that's one implementation detail that we'll see in a minute as well. And another thing is basically what Daniel said. Yeah, expand the root, visit all of its children before going to its children's children. And the reason this is good is because when we have DFS, which is going really deep into one area, if you have a situation where the thing you're trying to find is right next to you, you're not going to find it until much later because you're going to have to traverse deeply into other areas. So time complexity wise, like depending on what you're trying to achieve and the probabilities of those items being near you versus farther down the line, or how specific of something you're looking for, that's how you decide whether you want to use BFS or DFS in a certain situation. So going back to implementation details, what data structures would be best to use for BFS in terms of like how to make it work from a coding perspective? Bobby.
Alright, so it seems like you want to keep stuff in order, right? And I think that I remember from a couple lessons ago that queues keep stuff in order.
Mm-hmm.
So I would say use a queue for this.
Okay, okay. That's a good thought process. You want to keep things in order, but why do you want to keep things in order in particular? Since we're going to the nearest ones, what do you mean by order in that
Yeah,
sense?
so the earlier that you get to, so the earlier that you get, so the closer that a node is
Mm-hmm.
to like the root where you start, right? The earlier you're going to visit it in a BFS,
Mm-hmm.
and you want to be able to keep that ordering, because it's not like you can just, you need to be able to like keep track of where all the other children are
Mm-hmm.
of like the root, right?
Right.
And in order for you to make sure that you're going sort of like in this outwardly expanding thing, you're going to want to take the last item out of the queue before like going on to something next.
Right, right.
Yeah.
That makes sense. So did everyone hear that and understand what Bobby said? Basically said that the reason you want to keep track of order is because, first of all, the definition of breadth first search is you're going by what's closest to you, right? And to get to what's farther from you, you have to know what was closer to you, because then you can't get there. And so a queue is, in fact, the best way to do that. So I don't think okay, before we get to BFS, so I will draw something here. Okay, can everyone see this color? Is this good? Okay. So we have, a graph like this of A, B, C, D, E, F. Say we designate, so again, a key distinction between a graph and a tree is that we don't have a start place. So say we decide, okay, we're going to start here, right? Rather than maybe you would want to start here. It doesn't really matter. So if we start here, we have a queue. I'll write it here because so you can see. We have a queue. We'll put this first item in the queue, right? Now, the thinking behind it is we want to reach all its neighbors and then go to all of those neighbors. So this is kind of where you're going to start. And then as an exercise, we'll have you like think through like how exactly you're going to implement when you put something on the queue, when you take it off the queue, and how you determine you're done, basically. So actually, let's do that now because I think the next thing is covering DepthFirst Search. So how about we take 5 minutes and like if you want to talk, you can talk. If you don't have to. But basically, going based off this, how would you decide when you're ending, decide what's going on next, decide when to take stuff off the queue? Yeah. Okay, that sounds good. We'll keep going then. So yeah, basically, that is what you're doing. So you first put in like D, for example. That's where we decided to start. That's the item in the queue. So the while loop is while the queue's not empty, right? Is as you said. So the queue's not empty. So we take off D, right? You like take it off the queue, and now we're working with D. We're holding D, right? So now we want to add all of D's children. So in this example, we have E, so we'll add E. We have F, and we have A, right? We have added all its children in the queue. So now we would add, so since we have finished working with D and we have added all of its children to the queue, we don't just throw it away. We'll just like have it in a like visited array, for example. So let's call it like V for visited. We've seen D, and now we're done with D and we've added all of its children. So the reason we have a queue is because now we know that these are its children. We're going to see these first. Technically, like one may ask, like, does it matter if you had like EFA versus AFE and things like that? And in like the basic situation, it doesn't. But if you introduce like maybe a nuance, like oh we have edge weights and the edge weights are important, or oh we have I don't know. I think edge weights is a good example, or maybe different types of nodes. Those nuances can help you determine like which order to put them in. But for basic stuff, it doesn't really matter because as long as you have the first round of nodes you're looking at. And in this case, okay, now we go to E. E does not have any children in this case. And the reason we know that, if we didn't have this visited array, we would go back to D and add D back in the queue, just because D is connected to E. And we haven't really manipulated the graph. So because we have it in the visited queue, we know, okay, D is not supposed to be in here. We're done with E. So we pop it off. We realize it doesn't have any children because D is not considered connected. And now we move to F. We go to F, same situation with F, is just connected to D, and D is already here, right? Now we go to A. A is connected to C and B, and neither C or B is in the visited queue, so we'll add those. And then we're done with A, put it here. And I actually missed, you're also going to put E and F in here as well. And then as you're done, you pull C out, you do the same check, nothing passes, B out, the same check, nothing passes, Q is empty, so that's how you terminate. So I guess like anytime you're describing an algorithm, it's important to hit a few key concepts. One is basically where do you start, right? And in this case, like we don't have a root, so we kind of just pick a random root, right? In general, when you're talking about algorithms, talk about where you start. Another key part is where you end, right? So in this case, you mentioned that your while loop would be while the queue is not empty. And so you need to have a terminating condition when you're talking about it, and making sure that the termination condition is very specific to like the question you're being asked. And usually it'll be something like this, where especially in the DepthFirst Search case, like while this is not empty. And the last thing you want to do is making sure you check for, especially with graph problems, self loops or cycles or things that could throw off something in the queue, right? Because if you said this whole example, but you just forgot to mention the visited queue, the next question the interview would ask you is, how would you make sure, like, when you go to F, aren't you going to go back to D, right? And then you'd be like, no, you come from D. Like, you wouldn't go back to D. And they're like, how do you know that, right? So, like, it seems intuitive when you're explaining it, but then when you're actually coding it, per se, you would run into a lot of difficulties. And so it's important to kind of, like, throw that out there before they ask you. So it's better if you do that. Does everyone understand BFS? Good? Yeah, okay. Now we'll move on to DepthFirst Search. And so someone covered DepthFirst Search earlier. So let's talk about boolean maybe versus an array. So we need an array in this example to like catch for that little exception. So in DepthFirst Search, we might need a boolean. So why would that be? So think about, maybe look at the second bullet and you see, okay, we're using recursion. So usually when we discuss recursion, how do you stop a recursion, right? And boolean might be tied to that. Yes.
You have a base case.
Yes, exactly. So it's basically, I guess you don't need a boolean in particular, but basically you need something to kind of stop your recursion in the first place. So say, so again, DepthFirst Search is, instead of going broadly out and kind of taking every level, you want to go deep into one node, take that child, keep going until you reach the end condition, and then come back up if you didn't find it. So say we're on a map instead. Oh, I guess there's no eraser here. Can I use this paper towel? Okay. So we have start and T for terminate, and then maybe these are cities, A, E, B, T, E, A, C. Okay, so we're going to see if we can get a path from the start to the end, and we're going to use DepthFirst Search to do that. In this case, how would we use recursion to, I guess, bubble up the answer on where we're supposed to go? What's the next step we're supposed to take in this situation? A hint is, okay, so we know S is where we're starting, T is where we're ending, and we're trying to decide which way to go. So in order to decide which way to go, let's just, like, we have to kind of bubble up the answer to the start, right? So the start knows where to execute next, right? So if we, say we're looking just at this, just at T, right? Does T have a path to T? It does, right? Because it like that's our base case. You can have a path to yourself in that definition. Like if you start at t, can you end at t? Yes, because you are there, right? So let's call that function like has path. So we have has path tt, okay, and this will return true, okay, because that's our base case. Now we have b, right? Let's move up a level. So what would return if we have has path bt, right, from b to t? That would return true, right? Just because it does have a path. But the thing is, how would this know? Is because you're bubbling this up. So that's where the recursion comes in, right? So when you call hasPath bt, it'll go to t and then call it on this. So now you can kind of see how we're going to get to here, right? So we'll bubble up again. We'll say hasPath et, right? And then that will call this, which calls this, which returns true because that's the end, and then it bubbles it up. So now, if we keep going, you'll have hasPath all the way st, which will return true just because you reach the base and you go back up. So that's kind of like, that's how you would implement DFS in that way, but there are some like cases you have to think of. So do you guys want to like maybe take 5 minutes to think through the implementation details and come up with a more solid thing? Or we could also do it where someone comes up here and implements it, and I could pull up like IntelliJ and we could do that. If someone volunteers, so it depends on that. Okay, so how about we don't have anyone come up here? We'll just have, before we move on to the next thing, we'll just have you guys take 5 minutes, kind of take out a paper and try to roughly implement it, how you would kind of basically bubble up the answer that you're looking for. And then we can go over it afterwards. So we'll start again in like 8:32-ish, 8:33. Okay, so does anyone, oh, are you guys good, or do you want like 2 minutes? We're good? Okay. So does anyone want to walk me through basically what implementation you thought of? And again, I should have mentioned, since you are like, since I drew the example recursively, you could also do this iteratively for sure. Just because anything you can do recursively, you can do iteratively. But yes, anyone want to kind of walk through the logic? Yes.
I'll try my best.
Mm-hmm.
So you have a function which takes in 2 nodes, and for now I'm going to say a list of nodes that we've already checked.
Mm-hmm.
And so if the start node, or if node 1 connects to node 2, which is going to be your end node, then you return true, and that's like the base case. And so then if that's not true, then you move on to just like the general case, and then that's where you add the node that you're at to the list,
Mm-hmm.
and then you check the children of the node that you're at
Mm-hmm.
with the function.
Okay, I see what you're saying. So what data structure do you think would be good for that?
That's,
Yes. And so yeah, basically kind of like going on more on what you said, and kind of like hashing out the details. So you said basically this part as in the beginning, right? You said, oh, we have 2 items, like you're trying to find a start to end, and you have a visited array, right? That's good. So basically, I think you guys have covered this, but I don't know for sure. But when you have like a lot of recursive functions, a good structure of coding is to usually have like a parent function like this, and that calls your actual function where you're keeping track of things like what you've already seen. Because when you're doing recursive things, you don't want to like keep recursing on things you've already done and like use up too much memory and space, for example. So say like, say this was a more exhaustive tree, right? And E had a lot of children, right? And it had, or E had a lot of children, then A had a lot of children as well. if you recurse on E once, you're recursing on A by the description, right? Because you have to recurse on all of E's children, and by default, since you're recursing on A, you recurse on A's children. If you were to recurse on S, then you're basically doing that whole body twice, right? And so, does this sound familiar in what I'm saying? So basically, this wrapper that calls your actual thing that has the logic in it is usually a good way to do this. So in the wrapper, a good way to like mentally think about it for any type of function that's going to recurse, you have your wrapper, which you have like the basic things that the user will give you, right? The start and the end. Then you initialize what you need to from the given information, right? Like say you had a size, right? Size is 10 they give you, so you would initialize that as well. Then once you initialize all your inputs, which is done right here, then you want to have a structure that keeps track of things you'll be recursing on. So in this case, we can use a hash set just because you don't need more than the nodes you've already seen, right? In other cases, you might need a map because you need like a unique grouping, for example. So you initialize your data structure that will help you keep track of recursion, then you call your recursion. And this is what we're going to look at, is where your logic comes in. So that's over here. So we have the source, the destination, and we have the visited. First, like we have kind of like a little check, like if we've already seen the item, then we're not going to go and recurse again, just exit there. Next, you add the item you're visiting. That means you haven't seen it. If source equals destination, this is our base case, right? Like in this case, if we are at the end, right, and we want that to return 1. So this is our base case right here. And now this is where we want to recurse. So for each child, if we aren't at the destination node, say we're here at E, for each child of E, we would want to check if any of those children have the path, right? And if any of those children return true. So say you had E, and you had child B and you had child A, so you would call B and A, right? Because you're recursing through all the children, and those would again recurse through all the children, and that's how you would go through. So if any of those works, then you would return true because you have found it. And again, this is where the recursive call comes in. It'll go back in. If it's the actual base case, it'll stop here, return. If it's not, it'll keep going. So that's kind of how the recursive implementation works. And there is an iterative implementation as well. So does anyone want to like take a stab at it's basically what you said, right? So kind of building off that. How would you use the stack in the iterative approach? Yeah.
I think it's kind of like the DFS approach, but you just replace the queue with the stack. So when you visit a node, you add all its children to the stack, and then you pop one off and you visit that, and then you add all of those children to the stack. And then again, if it's already visited, you won't visit it again. But yeah, so that way it just lets you go as far as you can.
Right, and that's the key point. Like the reason you're not using a queue, right, is because you're not caring about the FIFO. You're not trying to go nearest, right? You want to go deepest, and that's why you have a stack, because you just take the most recent and then go again from there. So that's good. And the reason I only talked about the recursive was because this tends to, I wouldn't say it looks better, but I feel like usually if you have a recursive implementation, it's more impressive than just having the iterative implementation, but it's always good to note that both can happen. Like anytime you recurse, you can do it iteratively. So yeah, and we just covered BFS, but here is the implementation for it. So here, instead of a queue, like a queue is implemented by linked list. So you guys covered that already. So here in this implementation is just using a linked list rather than a queue, but you could use a queue as well. Then you have your visited array or hash set, and here, this is where the logic is. So we were checking like, oh, the queue's not empty. So queue's not empty. We're going to go inside. We take the first item from the queue, and then we're going to basically add its children. So if that's the destination we're looking for, we're just done. We return true. If it's not, then we continue on that item, put it in the visited because now you visited it, and go through its children and add it to the queue again, and keep going until you finish the queue. And this check is crucial because if you're not adding it to the visited queue, you're not able to check if you're doing too much, basically. Okay. Now we're going to go back, and how many of you guys have talked about tries or have covered tries? Yeah? Oh, okay. I thought they don't cover it in 201. I guess they do. They do. Okay. So, do you guys, I was going to cover basically a data structure again, so should we, like, do any of you think you need to cover it, we can go through it anyways, basically like the simple implementation. Let's go through it, right? Yeah. So basically, a trie is a specific type of tree, and anytime in interviews you're using it, it's usually for characters. So it's good for situations where, say, you need to look up a word, say you need to look up a prefix and any of the words that have that prefix. Say you need to look up words that start with a certain letter. Anytime you need to like find something that has to do with characters, it's kind of a lookup problem, kind of a character problem. Maybe you should use trees. Most probably you should use trees. So, not trees, tries. So let's see an example. So I'll draw an example up here. Okay. So we'll cover kind of like basically 3 basic ways of manipulating them and creating them. So first we're inserting, then we'll search, then we'll delete. So say we have A, B, C, D, and E, F, G. Okay, or we'll just do E, F. Okay. So first before we go into that, let's talk about what a node would be represented as if we wanted to store these in like a dictionary almost. So what would each node have to have? Or what do you think it should have? So we'll draw a node.
A letter.
Okay, so it has to have a letter, so we'll have a character. And then what else do you think it should have?
It's children.
Is children? Yeah. So we can do like So we can do children and basically, I can't reach that far, so it's basically a hash map. And why would we want to use a hash map rather than a hash set or an array, for example? Like what would we map? So in this case, say we have a node, right? Let's fake initialize this node. We have the character would be A, right, for this first letter. Children, hash map, what would we be mapping for the ABC? It's what?
It's weight.
It's weight? Like how many letters it has, you mean? Or what do you mean by weight?
Never mind.
No? Okay. Like, basically, if we just have A, and we're looking at this, right? We have 2 words that start with A, right? And we want them both to be mapped. In this case, when we say children, B is a child, right? Because it's the next letter. That's where we go from A, right? So we would want a hash map that's mapping basically a letter to another node, right? We have A, we're the current node. We're mapping, okay, I have a child B. Where's B? That's the value, the other node, okay, if that makes sense. So I'll draw it out to make it more clear, but basically these are the 2 things you need rather than just a character. And did you have a question?
Yeah, right. So the children hash map, that's your child nodes to, or
No.
so what's the first letter?
Yeah, this is actually like a character. I wrote letter, but it should be a character. So in this example, we have character A in the node. In the hash map, we'll have B mapped to like the node B, because
So the keys are the children.
yeah, exactly. The keys are just the characters that represent the node that you're trying to find. And the reason you have that is otherwise you can't really find the node, right? You know, like the child is B, but like you need a way to get to B, right? B is going to take care of its own children, right? You want to have like modularity in terms of what each node handles. Otherwise your node would be too big and that would take up a lot of space. So let's draw a node like this, right? And first we'll have the root, okay? So let's just initialize, like, you know, we don't need anything there. And this is, so when we draw this, we'll have this as the character and this as the map. And actually, I forgot to mention one other thing we would need. So how do we, when we're looking up these 2 values, right? We have A, B, C, and we have A, B, C, D. There needs to be a distinction on when we end, if that makes sense. So we would need a character or something that signifies we're at the end, right? Because if we're looking up ABC, we could go to ABCD, right, which is a different word. But if we go to ABC, that's also a word. So we need to make sure we're distinct, like making that distinct. So we also need a boolean that basically says, are you at the end of a word or not? So, yeah, so we'll have like a little boolean here. as well. So this is our root. We go to A, right? This is now our insert function. So we go to root. Does A exist in the child map, right? This is our child map. No, A does not exist in the child map, so we're going to add it, right? How do we add it? We add it here, and we in the hash map. So we go like child dot add A, and then new node, right, which is creating this. I'm kind of drawing too big, which will be a little difficult later, but we'll add a new node. And now, what is this new node mapped to, right? It's mapped to B. But right now, that's all we need, right, because we're done with A. Okay? Does that make sense? So you're at the root, you see A does not exist, add it to that map, and just add a new thing, right? Another check you would want to do is say you just had A, right? You don't have anything else. That's one word. That's the end of a word. So you have to do additional check on if you're at the end of the word. And if you were at the end of the word, you'd add like your little boolean signifier because A is your word and now you're done. Since we're not at the end of the word in this case, we don't add that. So we have A, add a new node. Now we move our pointer to B. We're at B. Now we're here. B does not exist in this map, right? So we'll add B. We add a new pointer, new node, and we are not at the end of the word, so we're done. We increase our pointer to C. We're at B. We check our new node. C does not exist in the map. We add C to the map. And now we see that we are at the end of the word because we have that check each letter. So now what we want to do is when we're adding C to the map and we add a new child, this child will be empty, which is fine, but we'll add like a little boolean indicator, which I'll do by like shading in the bottom of the box. So can everyone see that? It's kind of messy. So if theoretically we were trying to look up is ABCD a word, or is ABC a word, we go to A exists, so we go find it. B exists, so we go find the child. C exists in the child, we go find it. Are we at the end of the word? Yes, because this boolean is true. So we know ABC exists in the map. Now how would we add the word ABCD, right? So we start here at the root, we check the mapped nodes. We have A, right? So A exists. Let's go to A. A is mapped to B. That works because we're doing AB, right? So our pointer is now here. B exists. Let's go to B. And that's through the hash map. Now our next item is C. C is in the map, right? So that's correct so far. We go to the next one. Increment this. Now we're at D, right? D does not exist in this last map, right? Because for the last word, it was done. So we're going to add D to the map and just increase, make a new node. And now, since we're at the last letter, we shade it in terms of the boolean, right? So now we're adding a boolean because we are at the last letter. Same thing with E. If you had to go A, B, C, D, E, you would go here, add E, add a child, add the boolean. Now we've added these two in the map, and same thing with E, F. Here is E in the map, no, add it. Hash map gives you the next data structure, and F is not in the map, add it, next data structure, it's the end of the word, so we add the boolean saying we're at the end of the word. So that's kind of the insert function, and let's talk about how we would search. So based on this kind of visual, does anyone have an idea of how you would search for a word? Say I wanted to search, is a word?
You can start from the root,
Mm-hmm.
and then you would check if it's marked boolean or not, because you have to find the first letter.
Okay, so you're saying I start here, I check if A's there,
Yeah.
and then I see A, so now what do I do?
Well, you have to check if it's a word by the boolean value.
Okay, so I check the boolean value in this node, you're saying.
Yeah.
Okay, so yes, you are correct, because sorry, no. Okay. Instead of checking the boolean value at this node, that would be a little difficult because say if we made this boolean true, that means E is also a word, right? By that logic, because say we wanted to check for E, then we'll check the boolean, it's true. That means anything in this would be true. So you would actually go to the hash map, right, and check if the child is true, because the next node signifies if the current node is ended. Does that make sense? So if you had A, so in this case we have A, B, C, right? We had A, B, C, and this is the node, the Dth node is marked as completed. So you go to the next node and check if it's completed. And the reason you can do that, you might go how do you even know if there's a next node, right? Anytime we make a new node, so in this case we had A, B, C, D, we made the next node and marked it as completed. So nothing's in the map. So you never have to have stuff in the map, but you always need the boolean after the word to mark it as finished. So yes, that's how you check it. And same thing with A, B. We would go to A, we'd go to B, but don't check this node, check the next one, and there's no boolean, so we know AB is not a word, which is right according to this. Now, how would we go about deleting? So say we wanted to delete ABC, not ABCD. How would we go about doing that? Any idea? We want to make sure we're not deleting extra, so that's a little catch there. So basically, how you would make sure. Should I give you guys 5 minutes? Do you want to solve it, or is it like should I talk about it first? To you guys.
Wait, can you just like go down to the word and then set the end thing to false instead of true?
Okay, so in the case of ABC, can you like tell me which nodes you go to?
You would go A, then you would go to B, then maps to C, and then you would go to the next node and then switch it to false. Right?
Yeah, exactly. That's correct. So you would want to switch the boolean value here. So it's empty. So ABC is not a word, but ABCD is still a word, right? So that's correct. Now ABC is not on the map anymore. How about we want to delete ABCD? Now how would we do that? And this is a little more interesting in the case that we want to keep track. We don't want to have extra nodes floating around, basically, right? When we deleted ABC, we still had ABCD. You never had to delete anything big. You just switched to boolean. But if we're deleting something larger, how would we go about that?
Can you map backwards?
Map backwards?
Like, is it directed as in only one way down, or can you go back up the tree?
You could go back up the tree, but it wouldn't be by that way. You could recurse back up the tree, almost. So that's a hint, I guess. Like that was a good question. Simran asked, like, can you go back up, right? So you basically you can go back up. You'd kind of like recurse back up almost, but you can go back up. Yeah, so basically, if you wanted to delete ABCD, we'd have a lot to clean up, right? Because the only word we'll have left at the end is EF. So we go to A, it's following the same process as initially, right? We go to B, go to C, go to D. Now we're at the end, right? So normally we'd go to E and just reset the Boolean, right? Now, an additional caveat is when we reset the Boolean, which we should do, right, according to what we just did, now we're also checking, okay, the map's empty, right? There's nothing there. So that means this is not signifying the end of the word, nor does it link to other words. Why are we using this, right? So we can just delete this node, right? We can get rid of this because we reset the Boolean, nothing's in the map, we don't need it. We climb back up, we're here now. This Boolean is also now empty because we just deleted this word, right? And now when we deleted this node, just by how a map works, remember we were storing a children map of the letter to the node, right? And we just deleted the node. So this D is not pointing to anything, right? It's just there. And so we basically deleted the entry, right? So now this map is empty, and this Boolean is also false, right? There's nothing there. So again, we can go back and delete this one. By virtue of deleting this one, we again have the same issue here. We have C mapped to nothing, so that entry is now deleted, right? So C is gone, not touching anything, and now the Boolean is also false here, so we can delete this one. We go back up here, B is not mapped to anything, and now we can delete this one. And now we go back up here. Although the Boolean is false, it's mapped, like it has values in the map, right? So we can't delete it, but we delete A just because that was what was pointing to this. So now if we look at what we have now, we just have E, F, and word. So we just have this word left in it. So does that make sense? Yes.
Yeah, I just have a question about, like, what if you wanted to add the word FE?
FE?
Yeah, would you just add F to the root node and make another E?
Yeah, exactly.
Okay, so it's not a problem to have like it's not necessarily duplicated, but you do have like two E's.
Yeah, exactly. So the reason that is because then it would be very hard to keep track of, like, if you restrain, like, oh, FE, let's go FE, right? That might be difficult because you would never know where a word starts, right? Right now we know that all words start here, and all words are ended and signified by this. So that's why this is a good structure to have, like prefix lookups, rather than suffix lookups. You know, so it's not, if you wanted suffix lookups, maybe you could that could be a twist on a question, and you could just maybe reverse the words so they're backwards, and then do the same thing, right? And it could be very similar, or a little twist on it. But that's why you want to always start at the same spot.
And then what if you're like DAF? Would you map to a different F or the same F?
A different F. So it's a little, like, if you think, like, I like your point about, oh, you're making too many extra stuff, right? Because you'd have D, A, F. We already have an F. Can we map them together? The reason you can is because we're having the child map, and the child map is the link, right? So yeah, that's a good question. Yeah. Okay. Actually, before we go to some problems, let's talk about topological sort, which is an important topic. Have you guys covered that in class yet? No? Okay. So basically, topological sort is good for when you're trying to find the ways in which you can schedule something. So, for example, Bobby had a good example where if you have all your classes and you have the prereqs of those classes, so say you have 101, you can only take 201 if you had 101. You can only take 230 if you had 201. You can only take 250 if you had 201. So you can build a graph like that. And basically, topological sorting is a way to know which orderings are valid. So, for example, in the situation I just gave, you can take 101, 201, 250, 230. You could take 101, 201, 230, 250, right? So, just going off of that one real-world example, you can see that there are multiple orderings for a topological sort that could be satisfying, like, to the problem. Another example of where topological sort could be used that I always remember is, like, when you're trying to build dependencies. So say you have a compiler and you have different libraries, right? Certain libraries are built off of other libraries, so you first need to initialize them in the right order for everything to start working. So that's like a real-world application of topological sort, because you have to make sure you're building everything in the right order, just because things depend on other things. Otherwise, your program will crash, or the compiler just won't compile. So those are two real-world examples. So we can cover that. Okay, so this is a good diagram of the situation described earlier about class dependencies. So here you have the intro chemistry that allows you to take this. You can't take system biology without taking these two prereqs. You can't take this biology class without having math, which you can't have without this, which you can't have without this. So you have this whole network, and representing that network could be done in a topological graph, or a graph where you do topological sort. So earlier I mentioned the key distinction between a graph and a tree is like roots. So you know a defined starting point versus an undefined starting point. Here you could have a starting point here, right? You could also have a starting point here. You could also have a starting point here. It's not defined as one. So that's this kind of verifies that this is a graph. Okay, so going here. Okay. So we have a graph. Okay. Can one of you guys tell me where topological sort may start and where it would go if it started there?
Like, you mean after it was sorted?
How would you, what do you mean by sorted?
Like, if I was to, like, actually do my classes, like, how I would do it, or you mean the algorithm to sort topologically?
Yeah, the algorithm. Yes, what's your name? Kunal. Okay, yes.
Yeah, so I think it started at 0.
Mm-hmm. Mm-hmm. Okay, that's a good point. So you chose 0 versus, why did you not choose 8 here?
0 just provides a lot more
Dependencies?
options.
Okay.
So it is a dependency for all of them.
Right. So that's a really good way you decided. that's a more optimal way, right? Because if you build 0, you're by default going to all of these, right? In the actual sorting algorithm, it doesn't matter where you start in the sense that as long as it doesn't have anything pointing to it, right? So 0 would work and 8 would work. And yeah, because nothing goes there. Those would be good starting points. But if you're trying to do a more advanced algorithm where you're trying to get like the optimal running time, for example, or like trying to like knock down the most blocks with like just one thing, you should start at 0 because you based it off of that. So you start at 0. Now to build it correctly, where would you go? Like if you're thinking logically through it.
You probably want to go to 1 and 2.
Okay, so you go to 0, you go to 1, go back, go to 2,
And then 4 and
go back.
3 and 6.
Okay, how did you get to 6?
6, I went back to 2.
So did you go back to 2 from 0, or did you go from 4 back?
I went.
How did you?
So I went to 0 to 2 to 4 to back to 2 and 6.
Okay. So that's a good way of going through it. So now you ensured you only go to 6 once 2 is completed, right? And 2 completes after 4 is completed. Or sorry, before 4 is completed because you're building up. If that makes sense. But what data structure would you use to implement that? What would you say? Would you use a queue? What makes you think that the queue would be?
Because it kind of seems like
Breadth first search?
type
Oh, because you're visiting all the children?
yeah.
Okay. So that's a good, like, I see your thought process there, but although we're visiting the children here, how would we build it? So if we're thinking about, like, say these are classes, right? Where you would need this first, right? Say, on the other hand, I'm trying to think of an example. Basically, you want to go to the end of anything before you mark it as completed. So let me run this simulation because I don't think I'm explaining it right. So you have 0, you go to 1, you go back to 0, you go to 2, go to 4. So you can see how this is checking if you have any additional children. So it's kind of going fast, but basically it's going to 0, goes to 1, right? 1 doesn't have children, goes back to 0. Then it goes to 2. Okay, so this is, you see here, this is the call, and this is the ordering, right? They're kind of almost the opposite in a sense. Not opposite, but they're not in the same order. So we have DFS on 0, which should give you a hint to like what data structure there, rather than a queue, but very similar to a queue, a stack instead. So you have DFS. Now we go to, in this case, we go to 1. You could go to 3 as well first. So we go to 1. 1 has no children, so then we add it to the stack, okay? Then we go to the other child of 0, which in this case they go to 2 first. 2 has children 4 and 6, so it goes to 4. 4 doesn't have children, 4 is added, okay? Now we go back up to 2. 2 still has children, we can't mark it as completed. We go down to 1, or sorry, that's not 1, that's 6. We go to 6. 6 doesn't have children, so that means 6 has been completed, so we add 6 now. We go back up to 2. 2 doesn't have any more children. The children it does have are completed, so now we can add 2. Now we go back up to 0. We just finished 1, we just finished 2, and now we go to 3 in this case. We could go to 4 first, but 4 has already been marked as completed just by going through 2. So now we just go to 3. We see it, 3 doesn't have children, so we add it. We go back up. Now all of 0's children are complete, so now we can add 0, right? So we add 0. Now you can go to any other starting point basically. So this could be correct also if you took the top 5 and 7 and moved it to the bottom, because you could start there, if that makes sense. Yes.
Instead of starting at 2, what if you started at 4? That
Mhm.
would look a little different, right?
Exactly. So if you went 0 to 4, you're saying?
Yeah.
So say we went 0, 1, so we have 1, then we go 0, 4. 4 has no children, so 4 would be pushed, right? Now we go back up. Now we go to 2, right? 2 has children. it'll go here first, right? Or it could go to either child. But say it goes to 4 first. 4 is already marked as completed. So then you go back up to 2 and check again. And then you see, oh, it doesn't have this. Does that make sense? So you have to not only keep track of like the completed children, but you also have to keep track of basically you're keeping an array or a hash set of everything that's been seen so that you check, oh, I'm at node 2. For each child, has it already been seen? And if it's not, does it have children? So that's where the recursion is coming in. So Bobby, you were going to add to it?
Yeah, so was your question like what happened if we started on 4?
No, started on 0 but went to 4 instead of 2 first.
Okay, yeah, it would look different. I
Mhm.
just wanted to add that like it's really important that you start on a node that has nothing going into it. That's another way of doing topological sort. Actually, you pick a node that has nothing going into it, and then you like say like, okay, like I visited that node, and then after that, like you quote unquote remove it, as in like you remove all the, you conceptually remove all the edges coming out of it, and then you select a node that at that point has nothing coming into it,
Oh,
and so on and so forth, and then you reverse that as a result of that. So why would picking a node that has a vertex going into, that has an edge going into it, be bad?
It just means that something depends on it.
Yeah, it means that something depends on it, right? So if we started off at 3 and we said, oh, cool, 3 has no children, well, actually 0 still depends on 3. So conceptually, it would be like saying, oh, okay, well, like there's no classes that comps like 330 is a prerequisite to, so I can just start off with 330, and there's no problems with that. Or you might have some problems with that in real life.
Yeah, definitely. Yeah, this is also covered in 330, but very briefly. I think it's also covered in 201 briefly. I guess not.
I didn't think
No,
When do we
it's
cover-
not.
it's
230
fairly
maybe?
hard on 330,
I feel like it's mostly 330, but oh, and these are interesting. So I mentioned very briefly at the beginning you could represent using adjacency lists or adjacency matrices. So this is just basically like an edge map. So you have all your nodes. We have 7 nodes, so 7 by 7, and then 1 signifies that there's an edge between those. So in this case, we're using a matrix because it shows which direction it's going in. So this would be from, and this would be to. So we have an edge going from 0 to 1, from 0 to 2, from 0 to 3, like that. And the reason we're using this is just to show direction. And same thing with the adjacency list representation that was mentioned earlier. We have all our items. So for example, 0, it's mapped to 1, also to 2, also to 3, also to 4. So that's all this is showing. Yes.
So what's the rationale behind using a stack instead of a queue?
Sorry?
What's like the rationale behind using a stack instead of a queue?
So the reason we're trying to, so basically we're basing off how the order is on whether you have any dependent, like the end case is when you have nothing else, right? Like no children that haven't been seen, or no children at all, right? That's when you're putting it onto the stack. So when you basically reverse this stack, it can tell you, wait 1 second, let me see this.
Wait, so just to
Wait.
clarify, are you saying why are we pushing our nodes onto a stack for the topological order? Or are you saying, okay, yeah. So, like, the reason why is because
See ya.
of the way that we are sort of implementing this, right? So, if we were to mark things in the order in which we visited the nodes, then we would have to, like, reverse that and put it onto, okay, so to go through that example again, right? Actually, you might just run through the topological sort.
You mean clicking play or?
Yeah.
Okay.
Right? So with the way that we're doing it, we're not adding anything until it has no children. So basically what we're saying then is we want the order in which when we hit that, we're sort of saying we want the reverse. It's effectively like sort of a reverse order of what you visited the nodes in. And because it's a reverse order of what you visited the nodes in, that means that whatever is at the very end is like whatever like you put first into whatever your data structure is whatever's at the very least. Well, not least because this isn't a tree, but like whatever at the far end of the graph, right? So that means that whatever that you have there should be like deepest or come So, like, for example, if we instead used a cube, right, then, and we did, like, comp sci 101, 201, 230, 330, then 330 would be the very first class that we would take, as opposed to if we pushed 330, then 230, 201, 101, then 101 would be the first class that we'd be able to access. Yeah, when you take 330, depending on whether you have Demolia or not, he's going to teach a slightly different way. But I think this way is a bit easier to comprehend. He teaches it as adding it in the reverse order in which you visit them, not in the forward order of when you have no more children. The two are equivalent, we can see that, right?
Okay.
But that's sort of just why we use stack, because you're doing a lot of reversing. I know it's kind of confusing, but I think that if you just think about it in terms of like Duke's CS prerequisites, it makes a lot more sense.
Can you say how Demolia teaches it again?
Yeah, so he first introduces the concept of a strongly connected component. And then he says, okay, so we want to start in a source strongly connected component. And then basically we just try to go to all of our nodes, take the forward order in which we visited them, and then reverse that and stick that to the back end of our topological store ordering. So I think that's less intuitive than this, especially because, well, with the tools that we have, the only visualization tool we have does it in this way. So that I think that also helps. If you want to, we can post a link to this inside the slides, and I'll play around this a bit more. This is kind of a niche topic, but I think that a way to make this less scary is just to realize that this is just a small variation on DepthFirst Search. But it's a very useful variation. Think of it almost as an application, I guess.
Another interesting point is what could cause, in what situation, given a graph, would you know you can't run topological sort?
If there's like a cycle.
If there's a cycle, why?
Because then you keep cycling around. Like you wouldn't ever get to a point where there's no children.
But aren't we also checking if it's already been seen?
I think this comes back to what we were initially saying, where you need to start at a node that has no parents. So if a node has like any sort of, if the graph has any sort of cycle in it, then at some point a node will be its own parent. So you need to make sure that there's no cycle in it, which, is that coming up?
I can talk about it.
Yeah. And one more thing, I know they all probably can see this from all the examples being like directed graphs, but you can't, it doesn't make sense to do a topological sort on an undirected graph. Because then, like, if you think about it, an undirected graph is just a directed graph where every edge goes both ways, and that means that every two nodes forms a cycle at that point. So, yeah.
Wait, are we actually going to code the topological sort algorithm?
We can. We weren't going to. Because
Okay.
we're also going to talk about, like, Bobby's going to talk about heaps.
Okay.
Yes.
What are dates back in that picture?
Oh, here? You mean with the nodes?
Yeah.
Let's see. F is the most, I believe it's the most nested. Wait.
It's
the ordering.
pre-first.
It's the ordering, right?
Yeah.
Oh, yeah. Okay, it's basically the, like, yeah, when it starts versus when it ends. So, like, on the first iteration, we're starting 0. Second iteration, we start at this, right? Third iteration, we're here. Fourth iteration, we're still here because we ended it, right? We, like, checked if it has children. And then we go back up. So this ends on the 5th iteration. Do you understand what I'm saying? It, like, opens because it has children, right? You're still in it. And then when the children are done, it comes back. Now you're closing, right? So that's why this opens on 3, closes on 4, because you just check if it has children, doesn't, right? Then you go to 5, then you go to 6 because this also doesn't have children. 7, you just start at any other thing that has nothing going into it. So it could have been 2, or it could have been 1, or it could have been 3. 7, 8. Yeah, because this has already been seen, so this also closes. Yeah. Okay. Okay, so let's go back to this. Okay. So now we see that cycles are pretty important in graphs we're doing just because like certain algorithms won't work if you have a cycle. So how logically would you check if there's a cycle that exists? Mm-hmm.
You could keep reversing until you like children until you get back to yourself.
Get back to yourself. Yeah, yeah.
Like
So
the same
okay, so if you have A, B, C, and C is pointing back to A, you recurse on A, or sorry, you go recurse on C, B, A, and then we go back to C, and then we know there's a cycle. That's what you're saying. Okay, that's correct. So I don't know where I put the link, but I had a link. Is it here? Oh, I had a lot of links. Okay, maybe it's not here. Okay, I actually. Oh, sorry. Okay, I don't have the link. Never mind. So I was going to talk quickly about some things you might see in 330, which among those is detecting a cycle, because I don't think that's covered earlier. But basically, detecting a cycle is determined on like what kind of graph you have. So you have an undirected graph versus a direct graph. There's different ways of detecting a cycle, just because you could have a cycle more likely in an undirected graph if you're defining it like that. So one algorithm is, say you have 3 hash sets, okay? One is a hash set of items you've already seen and visited, so they're completed in that sense. One is a hash set of items you are currently visiting, so they're in progress, and then you have a set of items that haven't been seen yet, which is basically where everything goes in the start. So if you want to think of it in terms of colors, you can think white is like you haven't visited, haven't seen, gray is in progress, and black is like you have completed that and it's terminated. So say you have a graph and you start at the first item. You go to its children, right? Now, since you're at the first item, you add that to in progress, right? Because you've seen it, you're not completed with it. You add it to in progress. Now you go to its children. You see it's all its children now. All its children are moved from the not visited to the in progress section as well, right? Now you go to those children, right? And you see its children, right? Those are also added to in progress. Say now you have a loop, right? So I'll draw this out so it's more clear, right? We have A, which has children B and C. And then let's say this has D, which connects back to A, right? So we have our 3 sets. We have so not seen, visiting, which is currently, and then done. So we start at A. Initially, all of them are here. We are visiting A now. It's moved, right? Now we go to its children, B, C. B, C are now, and D. D is also connected. So B, C, and D are now being visited. So now we're done with A, right? Or actually, we're not done with A. We'll keep it here because we could have maybe an E here. So we are only done with A if we're done with E. So we go B, C, D. Now we're visiting all of these basically, right? Because we're not done with A, and now we've seen these, and we're not done with them. Now the loop detection comes in, and when you're checking what set each item is in, right? So E is the only one not seen now. When we go through its visiting queue, right? We're currently visiting B, D, and C now. We go to B, and we add E to the visiting queue as well. When we go to D, and we're adding its children to the visiting queue, we're going to go to this edge, right? Because this edge has not been traversed, right? Sorry, go ahead.
Wait, so D or A points to D or no? Oh, okay.
Sorry, I should have clarified that. So this is a cycle, right? And now I didn't clear that up. So we have A in the visiting. We point to D actually wouldn't be here in this case. I was going based off of an undirected graph, but in a directed graph, we add A, visiting B and C, right? Now A, B, and C are things that are like in progress right now. Now we are going to go to B, right? E is now in progress because we're seeing it. E has no children, so E is marked as completed because now we're done with it. It's not being visited anymore. We go back up to B. B has a child D also, so we're adding D to visiting. And now let's go deeper into D, okay? D has a child A. A has not been not seen, right? That means it's been seen. It's visiting. That means we have a cycle, right? I feel like I didn't explain it very clearly, but basically you're using 3 different groupings to tell if you've seen something. Because now when we go to this edge is untraversed. That's why we use it. We go to A, and A is not seen. Otherwise we'd drag, like the reason we're checking in the code way is we're trying to take A and move it here, right? If it hadn't been seen, we could do that, but it's not here, right? So since it like map hash set dot contains A is false, right? Then that's our sign that we know that A is either visiting or done. It can't be done just because like in our situation we haven't finished the children, but if it was done it would be marked as well. So this is like one way you can detect a cycle because you know that, oh, since I'm at D and D's children is something we've already seen in some way, that means we already reached it, right? That means there's more than one way to get there. So that's how you can detect a cycle. Coding this is pretty straightforward. Just because, like, just if you make sure you have all the if statements correctly and you're adding them to the relevant sets correctly. So, yeah, if you did another example, it would be the same as well. In this case, we arbitrarily went to B first and then added E instead of going to C, but you could do the same thing. Go to C. C would be marked as completed. That's a move. Then you go to B, same thing, and then you go to D. So that's one way to detect a cycle. You can have different cycle detection algorithms, and I guess the uses in everyday life depend on kind of like what kind of cycles you're detecting or on what types of graphs. But this is specifically for a directed graph. Have you guys heard of DAGs, directed acyclic graphs? Okay, so basically, like it's this term right here. So this is the directed cyclic graph, right? Cyclic means there's a cycle, and this is directed because you have lines in your edges, like you have a direction. Directed acyclic graph would just maybe like now it's a directed acyclic graph. There are a lot of like algorithms that apply to those, and if you think about it, you could run topological sort on this, right? This is a directed graph. It's acyclic. That's what a topological graph was right here. It was all directed and it was all acyclic. Otherwise, it wouldn't work. Bobby, did you have something to add?
So one more thing to mention. Every single tree that Gung talked about last week was a directed acyclic graph. It was directed because once you went to a child, you didn't know what its parent was anymore, and it was acyclic because trees have to be acyclic by definition.
Mm-hmm. So, should we like talk about queues now, Bobby, or
Yeah,
or not queues? Sorry,
let's talk about
heaps.
Um,
Oh, and going back real quick, this is basically the C dependency thing mentioned earlier for the topological. So, say you're trying to compile this, right? This program, Hello World. You have all these items you have to make work, and they're all dependent on other things. So, that's basically just another diagram, but.
All right, cool. So before I do that, there's actually one more thing. And this was a problem that the reason why I wanted to introduce this problem is because it's a problem that does not seem anything close to being a graph problem, right? And I give you an array of unique integers, and I want you to tell me if it's possible to like rearrange the integers in such a way that every 2 consecutive elements sum up to a perfect square. So like, for example, if I gave you the array like 4, 5, or 4, 20, and 5. It's possible to rearrange it because like you could say like, you know, like 4, 5, and 20. And in that case, like 4 plus 5 is 9, 5 plus 20 is 25. Both of them are perfect squares. So initially your first instinct might be like, this is a sorting problem, right? But what property of sorting are you really looking at? There's a way to do it, and it involves graphs. Basically, you take every single number to be a node, and then for every pair of numbers, you say, okay, if number A plus number B is able to be a perfect square, then I draw an edge from A to B. And you do that for every possible pair of numbers, excluding like the numbers themselves, right? Because you can't use the same number twice. And at the very end of that, now that you have this graph, you say, okay, now is there a way for me to traverse this graph such that I hit every single vertex, but I never have to hit any vertex twice? Like you hit every single vertex exactly once. So there's a special name for this. I don't know if y'all have gotten to this in 230, but do you know the name for this traversal?
No, I thought it was just going to be a acyclical, like, directed graph.
No, so the thing that you're trying to look for here is actually called a Hamiltonian path. And you might have heard a variation of this. If any of y'all play chess, there's like a famous puzzle that's like, is there a way for you to like move the knight like around the board in such a way that it hits every square exactly once? That's another example of a Hamiltonian path, right? So this is showing you how a lot of problems might not seem like graph problems at all, but you can formulate them as graph problems. I was once given a very interesting problem that involved like strings, but it turned out to be a graph problem because it involved a form of topological sort. So always be on your toes. Just because something wasn't given to you in the form of a graph doesn't mean that you can't transform it into a graph. And as Ashka showed you with the tries, a lot of times you'll be asked to implement your own data structures just from scratch, and you should be comfortable with being able to do that quickly as well. Like if you're really good at like, you know, what you do, or if you use a language where it's like more natural to like define classes, or like less wordy, like basically not Java, then you can define new classes pretty quickly.
Wait, would that have to be done in n squared time?
So the Hamiltonian path problem is NP hard, or it's NP complete. So like finding a Hamiltonian path is not in polynomial time.
Okay.
It's in exponential time. So think about it this way, right? The worst case scenario is you literally just try every permutation of visiting the nodes in whatever order. And like that's really, really bad. Basically, if you don't know what the format of the graph is like, you're not doing much better than just random guessing. But I don't think they'd expect you to implement like an efficient Hamiltonian path algorithm. They'd probably just expect you to just make some sort of like very crude version using like a DFS. Okay. Yeah. So.
Why could you not just run DepthFirst Search and say like, why haven't you hit this twice?
Like run DepthFirst Search and say why haven't you hit this?
Like if you run into a node you've already seen before, like
Yeah. So the problem with that is a node it's perfectly legal for a node to have many numbers that lead to it. But as long as you don't take more than one of those paths, you don't have to. So like DepthFirst Search, you're exploring every possible path to that node. So you would just fail on that.
okay.
So let's talk about heaps. I was gonna try to do this at the end of Gung's lesson, but luckily because Gung covered a lot of DFS and BFS in his lesson, we didn't need to cover as much on graphs. So we're gonna come back to heaps now. So heaps are items that look sort of like trees, but they're not like trees. This is an example of a binary heap. In reality, a heap can have any number of children. But the important part of a heap is the heap property. So you remember how in a binary search tree, it was that every node to the left of the current node is smaller than the current node, right? And every node to the right of it is greater. Well, heaps sort of simplify that property because instead of like a left-right relation, you have more of an up-down relation. And that up-down relation is, for a max heap, like the one that we have over here, so first of all, the biggest item is at the top, and second, that every child of a parent node and all of their descendants, they are all less than that parent node. So there are two different types of heaps. There's a min heap where the item at the heap is the smallest, at the top of the heap is the smallest, and there's a max heap where the item at the top of the heap is the largest. So heaps are really useful because they can be used to implement like things like priority queues, right? Where with a regular queue, you would say, all right, whatever's first in is going to be first out. But with a priority queue, you could say, all right, well, whatever is smallest inside is going to be whatever is first out. So you can think of how this would be useful in many like real life situations, right? Like if you have like a person with like, if you have like a a VIP customer like in a checkout line, for example, going back to the old like example, then you would want for them to be able to cut to the front of the line more quickly. But more importantly, heaps can be used for like several things, including sorting. And one of them and that's called heap sort. And the way that heap sort works is you take all of your items in your array and you throw them into a heap, a min heap, or a max heap, depending on like whether you want to go through the array forward or backwards. If you use a min heap, you throw all of the items into the array, and as you step through a new array, that's your return array, you pick the top of the heap every single time. And you would see, because the top of the heap contains the minimum item in the heap at every single moment, if you keep picking the minimum out, you're eventually going to pick them out in sorted order, right? So that's really magical. How do heaps work? We're not getting into that in this course. That's really complicated. Basically, like heaps are one of the harder data structures to implement because unlike trees, where like you can sort of like just create your own node and all of that sort of stuff, with heaps, it's a lot harder to keep track of who your parents and who your children are efficiently. Because this sort of ordering of making sure that like every single parent is greater than every single child, that's difficult, especially when you have something dynamic. And I just want to stress that with heaps, it's really, really useful when you want to keep a dynamic list and keep the minimum or the maximum of that. If you had just a static list, then you could just pass through all the items once and find the minimum or the maximum or whatever, right? But with a heap, the power really comes through when you don't know how many items you have. And I think that really shines when you're, for example, trying to find the median of a stream of integers. So say that I give you an infinite stream of integers, right? You don't know how many of them there are. I want you at any given point to be able to tell me the median. So this is a lot harder of a problem than it initially sounds like, right? If I get asked for you to give me the average, then you could just keep a running average and then like just weight the average different, like recalculate the average every single time, given your current average and one new item, right? Because at every single point, if you know what the average, like you could just keep like a total sum, right, of all of the items summed together. You could keep a count of how many items there are, just divide it to, and all of a sudden you have your average. But a median is not something that's really like natural in some senses of the word, right? We can't calculate it simply with just like the sum and the number of items. So instead, what you might think is, well, there's two different types of heaps, a min heap and a max heap, right? What if we put all of the really big items into the min heap and all of the really small items into the max heap? So that way, the top of our max heap is the biggest small item, and the top of the min heap is the smallest large item. You can think of it sort of as like a triangle almost, right? Because we saw before that like this thing has a max heap, and it's like, it has 100 at the top, whatever. So that can be our bottom. The largest item is right here at the pinnacle of the mountain. You then invert that, and you say, well, the smallest item is going to be right above it. And that smallest item is going to contain stuff that's greater than the median. So that seems simple enough, right? But there's a couple of implementation details that are really, really important with it. Namely, that you need to make sure that everything in your min heap is actually really big, and you need to make sure that everything in your max heap is actually really small. How do you do that? Have an idea?
Can you compare it to the current median?
Sure. You can compare it to the current median. What you can also do is you can compare it to the current median, and if the biggest item in your max heap, if the smallest item, so if the biggest item in your max heap, which again, your max heap has small items in this example. It's kind of confusing, but your max heap has small items and your min heap has big items. So if your biggest small item is bigger than the median, then your biggest small item needs to go on this side. And the median needs to go on this side, like the new number that you just got. On the other hand, if your smallest big item is smaller than like the median that you calculated previously, you need to move that guy over here, and you need to push this guy that you just got into the min heap. And you just want to make sure that both of these are of equal size or differ at most by 1, because that's the whole beauty of it. You need to be able to make sure that these two are equal, so that way like you're actually computing the median instead of just, a difference between a big small number and a large big, or a big small number and a small big number. Yeah.
So in this case, we're getting feeded the list of numbers dynamically, right? Or
Dynamically, yeah.
So when we have one number, can you like walk through like how it starts?
Yeah, sure. So let's say that we have, let's just draw our hourglass figure, right? And so let's just say that we have 1, 3, 2, 6, 4, 9, right? So when we have 1 and 3, then the median is going to be 2, right? You're going to average it. When you have 1, 3, 2, the median is going to be 2. When you have 1, 3, 2, 6, it's going to be the average between 3 and 2, so 2.5. And then when you have 1, 3, 2, 6, 4, it's going to be 3, right? And then all of these together, I don't want to do mental math right now, so I don't know if we're gonna get there. Point being, okay, so we start off with 1, right? And so right now, just by convention, let's put 1 into the bottom. And then just by convention, let's put 3 into the top. And let's say, okay, let's call the median. Well, these two are of equal size, so I'm going to just average the 2. So then we add in 2, and we say, okay, all right, let's add in 2, and by convention, let's add 2 to the bottom, right? Okay, so now we've added 2 to the bottom, and now we say, okay, well, now let's take a look at whatever is larger right now, right? And as long as we can keep a convention that like one of the two is always larger than the other, then we're fine. And I think that with the way that we're setting it up, it always needs to be it always needs to be, let's just keep it as the bottom being the bigger one. So we added 2 in, but remember that this is a max, and this is a min. So that means that when we add the 2, we actually put 2 at the top and then 1 goes somewhere down here. How does that happen? Nobody knows. You'll find out in, I don't even know if they teach this in 330 anymore. But yeah, anyway, so then you sync this and you say, okay, cool, it's this. And whenever the bottom heap is larger, then you always return the larger ones on top. So then we say the median's 2, all right? So then, now we get another item, and that's a 6. So then we say, okay, so we have a 6 in there, and we want for us to add it to, when these two are tied, we want to add them to the, when they're tied, we want to add it to, okay, so we had the existing median, right? We had 2. And we say, okay, well, 6 was larger than the previous median, so we're going to add 6 to here, and 6 is larger than 3, so 3 is going to stay at the bottom of that. So now that these two are equal, when we call the median, it's going to average these two, and you're going to get 2.5. And then after that, you add a 4, and you say that 4 is also greater than the median. So you put 4 as the one over here, and then you take a look at whatever's larger, and the larger one, the one with more items, is going to be your min heap. So you take a look at the median of that, and that's 3. And then finally, you add 9, and you say that 9 is larger than the current median. So you add 9 over here, but all of a sudden you have too many items on top, right? So what you do is you take the item from the min heap and push it into the max heap. So all of a sudden you have 3, 2, 1. And over here, your min heap minimum, that becomes a 4. So over here, you average these two and you get 3.5. And I think that should be the answer, right? Because you have 1, 2, 3, 4, 6, 9. So there are 6 items. You take the 3 and the 4, you average them, and you get 3.5. So median of the stream of integers, pretty hard problem. I got it at an unnamed transportation company during my freshman year when I still didn't know about heaps. I completely failed it. Kept insisting that like finding the average was like good enough, and he said that's not the question I asked. Yeah, it was not a fun time for anyone involved. I've called back 3 years in a row. They still haven't called me back. I think they're just salty. All right, so I have one more thing that I wanted to talk about. And that was, hold up. Wait, how do you get to the Catalyst overall folder?
Okay, open it in your tab.
Okay.
And then go to Catalyst folder. Like there's a folder.
Catalyst folder.
And then it's yeah, that one.
Okay, cool. All right, so this is going to be a little bit of an addendum on what I talked about in the very, very first lecture with binary search. So how many of y'all were there? Great, awesome. So I have just one thing that I want to add to the very end of it. So I remember, Daniel, you were like, wait, I don't understand like the peak finding one, right? And I think that in large part it was because I didn't explain the prerequisite behind binary search well enough. So the very first thing that I did wrong was I forgot to say like, yo, binary search needs to work on sorted items. I straight up just did not say that, which I alluded to, but I didn't actually say. The second thing is that saying that binary search works on sorted items is not exactly correct. So here's the actual when to use it for binary search. So you have an array A, right? And for every index I, for all of the indices that are less than I, you can guarantee some property about every single thing that comes to the left of I. And similarly, you can guarantee that something is true for every single thing that is greater than I. Normally in a sorted array, that's that everything less than I is less than or equal to, like, you know, the index, whatever's at I, and everything greater than it is greater than it. But as you can see, there's some stuff that is a twist on this, right? So the first one that we did was called bug hunting. And that was where we had to find, I think it was the first version, the first bad version of the software. So what are our guarantees there, right? So for all of the indices that are to the left of I, like is good cannot be less truthful than it. That is like, you know, if it was already good, then it can't be not, or sorry, like for all the indices less than it, then like if this was if I was false, everything to the left of it has to be false too. If I was true, we have no guarantees. But for all the indices to the right of I, if I is false, you have no guarantee. But if I is true, then everything to the right of I is also true. So that's the sort of guarantee that we're talking about. That's the reason why we can use binary search. When we're talking about peak performance, right, let's take a look at, you know, case-wise. So you're at I. If there's an upward slope ahead, then for everything to the left, you don't know anything. But you know that for everything to the right, if you're on an upward slope already, it will either come down at some point or it'll run into the end of your array. Similarly, like if you're on a downward slope, then you can't say much for whatever is in front of you. You don't know if that downward valley will ever pull itself up. But you know that behind you, you'll either come down from a hill or you'll run into the beginning of the array. And if you take a look at the updated code that I sent over there, basically it just checks the endpoints first to see if like the endpoints can immediately be like a solution to it. And then after that, it does the binary search just as you would expect. And this works regardless of how many peaks and valleys there are. If there is indeed just one peak, like the one that we proposed, where it was just bitonic, then this simplifies to, you know, if you're on an upward slope, you know the mountain's ahead of you. And if you're on a downward slope, you know the mountain's behind you. All right, so finally, guarantees about this don't tell me the odds problem, where we were trying to like build a random number generator out of a PDF. The guarantees of this are really simple. Basically, the guarantees of this is that the CDF is sorted, and that's it. The hard part of this problem wasn't from recognizing that binary. The hard part of the problem was recognizing that binary search could be used, but the reason why it was hard isn't because like you eventually had to get it to a sorted order. The reason why it was hard is because you had to transform it from something that could be entirely random into something that actually is sorted. And taking that conceptual step from the PDF to the CDF was a difficulty there. So I thought about this a lot, and honestly, I wouldn't have added this if like Daniel and Brian hadn't like just come to me afterwards and just grilled me basically on like why this made no sense. And I will admit, like, I didn't manage to explain it very well in the first like lesson that we ever had here. But hopefully this clarifies some things, and I hope that y'all continue to come with feedback like this, because that's the way that we're going to improve it. This course, that's the way that we're going to wow them when we have the house course for next semester. So I think that's all the time that we have left. So thank y'all for coming.